as you may know, is about freedom of design, and the architects love that. And also people living in this house, I absolutely love this shower. There wasn't any chance to take a shower when we were there, but it's amazing. And this is something that if we want to do it in a traditional way of construction, it's gonna cost us a lot. And it needs very special skills and produce a lot of formwork base, etc. But during the construction, you can just have that. And the next job, you can just change it and customize it. It's not gonna cost you anything. You don't need to have new formwork, etc. So it's freedom of design is one of the key factors. I mean, there are other things that we are still working on it. It's still the printing material that we're using is not environmental friendly. The process needs to be optimized further. There's a lot of false claims in terms of low cost and things like that, which maybe happen, but at least at this moment, from my understanding, is still needs a little bit of work to get there. So this one hopefully would be the next project. So if I return next year, and if this project happens next year, I can talk about this one a bit more. So it's a holiday park. As you can see, the conceptual design is to have different 3D printed houses in one of the regional areas in Australia. Okay, so what we are doing in terms of research in construction 3D printing, we've been developing materials, as I discussed, for 3D printing for quite a while. So that's, and this is not just for in the lab environment. As I mentioned, when you go to the field, on-site printing condition is very different. You got very high drying shrinkage, the hydration of the material would be challenging. You may develop cracking, those kind of things are the thing that you don't see it in the lab environment, and it's just very new to us. We've been seeing it during our field trial, and we've been working on it. We have done very good improvements in terms of limiting drying shrinkage cracking in our field applications, but still there are some other projects that's coming that we can work better on that and have a better understanding of the effect of the environmental conditions, especially for on-site printing, on shrinkage, hydrations, and durability of the 3D printing material. In terms of the structural engineering, we've been very keen in terms of using reinforcement, automated use of reinforcement. And these are one of the key areas that are developing at the moment in our lab. In terms of design, structural design optimization and modeling, this is another thing that is continuing. We just started on that. And also quality process optimization and AI, which again is something that we just touched on. So some of the projects and some of the work that has been published. So this work with my PhD students on shrinkage behavior of cementitious 3D printing material, effect of temperature and relative humidity. So in this project, we wanted to look at how we can get a good understanding of the shrinkage that mimics the environment, that especially for on-site printing, and in condition that you don't have any formwork, because the standard shrinkage measurement, both for ASTM and BS, the kind of major standards that people refer to, keep the samples inside the molds for at least 24 hours. And for 3D printing, most of shrinkage is happening during that 24 hours. So it's not really representative of the shrinkage that is happening in this environment. So In this study, we just took out the samples 4.5 hours after being mold to get like a good initial setting and stiffness, so we can easily take it out of the mold. And then we put it into different temperature and relative humidity of 24 degrees and 50%, which is the standard, and also higher temperature and higher humidity and higher temperature and similar humidity. And then we monitor the drying shrinkage over up to 90 days and even more than that. We also looked at the sand to cement ratio. So higher amount of aggregates can limit the amount of the shrinkage. And so we looked at how we can increase the amount of sand, but still the material can be printable, and how it would affect the drying shrinkage. So the first thing that we notice in terms of the hydration and stress development of the samples that hasn't been properly cured. So the control sample has been sitting in the mold with a good sealing for 24 hours. And so and that first 24 hours is vital in order to get strength for that. And if we take out the sample, and this is a things that happen in the 3D printing environment, and depends on the temperature, humidity, and wind condition, etc. Some of those 3D printing projects on site, the mortar might be severely underhydrated. And as you can see, if you take out the samples and put it in different conditions, we get much lower strength. If the humidity is good, so if the area is humid, that can compensate a bit. But if you put the samples in a low temperature and 50% relative humidity, as you can see, the strength development is less than half of the same material that is properly cured. The other thing in terms of the shrinkage and mass loss. So here you can see there are two things. One thing is that the shrinkage that's happening in the first 24 hours, which is not shown here, but in the first 24, 48 hours, the amount of the shrinkage is much higher for free-formed sample compared to the cast sample. And this is not mainly based on this study. I mean, we are also using other study using strain gauges in real conditions in order to understand that, and this is our observation. But the other factor is that because the samples are underhydrated, so there is not enough water in the sample, and that lack of the water in the sample kind of stop any those capillary pressures by losing of the water over time. As you can see, for example, for control sample, it's just evolving until 28 days and then plateaus. But for free-form samples, you can see just kind of gradually moving. So it just at the same time it's unhydrated, getting some water from the environment, and also the drying shrinkage happening. And you can also see that in terms of the mass loss. Normally, for normal concrete drying shrinkage, when increased, you also have the mass loss at the same time because the water is evaporating. But for printing sample, you can see it's the opposite because it's very unhydrated. So it gets the moisture back, some hydration is happening, some of the product develop. You also have the carbonation shrinkage as well. So some of those unhydrated cement starts getting carbonated. And that's the reason that you got this kind of a very unusual behavior for 3D printed samples in a free-form condition. Another study that's, again, our PhD student Mohsen has been working on, and is recently submitted. So it's based on the geopolymer nanocomposite for 3D printing. So we used lead smelter slag to partially replace natural sand. And also we used two nanomaterials, which is nanoclay and graphene oxide. And again, we put it in the similar condition. One condition is properly cured, another condition, take out the samples from the mold after 4.5 hours and just put it in a different environmental conditions so to better represents the free form condition of 3D printing. So if you look at on the left is just the standard condition of curing. You can see replacing lead smelter slag will increase the strength of the material, and also adding graphene oxide and nanoclay, again, helping in terms of increasing compressive strength of the sample. But if you put it in the free-form condition, it's going to be another scenario. So that underhydration, that lack of water that is evaporated in early hours, it really affects the performance of those nanomaterials that we put in the sample. As you can see, they are not contributing or even slightly decreasing the strength in those samples. So that's keeping of the water in the first 24 hours inside the printed sample is vital in order to strength development, and also if you use any other additives as such as these nanomaterials to help with the strength development. So you may ask why we are using these nanomaterials. What's the purpose of that? So geopolymer material normally is like it's not that thixotropic. The property that we really want in terms of the rheological requirement of 3D printing, which if you're not familiar with this rheology term, so the structural buildup and the yield stress buildup of the material, especially at early ages, is not high. And we need that in a free form condition of 3D printing because we're putting loads of self-weight of those 3D printed layers on the bottom layers. So they need, as time passes, they need to get some early strengths in order to build up on that and support the successive layers. So as you can see, adding lead smelter slag, it helps with that early strength development, and adding those graphene oxide and nanoclay, it also helps. And graphene oxide, as you can see, it's pretty good in terms of that. And if you increase the percentage, you can even get better up to some limit, obviously. Otherwise, the material is not going to be workable or extrudable.
Dr. Kashani?
Can you hear me?
Yeah, it's audible now.
Okay, I think that my screen is still frozen, so
Dr. Kashani, your screen is also not visible now.
I think there is some internet issue with the speaker, so he got signed out. Just wait for 5 minutes. Let's see.
sorry.
Yes, Dr. Kashani,
Yes.
please continue. No problem.
Yeah, sorry. My screen just frozen, so I need to restart my computer. Okay. Okay, so again, apologies. So I was talking like we use the nano clay and graphene oxide in order to get better strength buildup that we need in terms of the buildability of the geopolymers, as you can see in this graph. In terms of the drawing shrinkage, using of Graphene oxide helps with reducing the dry shrinkage in normal curing condition, opposite of the clay because of extra water absorption between layers of the non-clay. And also, as you can see, using the leather smelter slag as a red lines here also help reducing the dry shrinkage compared to normal. So again, if we put the samples outside of the form, outside of the mold, you can see different conditions happening. And actually, those nanomaterials are not very helpful in terms of mitigation of the dry shrinkage. As you can see in here, the free-form condition, addition of those nanomaterials actually kind of exaggerates the drying shrinkage of the samples. And the reason for that, as you can see in these SEM images, the left two columns are for normal curing condition, and the right two columns is in the free-form condition. And in free-form condition, you can see a lot of unreacted material, a lot of microporosity, capillary porosity, and all of those things is because of the underhydration and the water evaporation at very early stages, which affected the trends of just contributed to high drying shrinkage. But on the other hand, you can see it's a better microstructure in the normal curing condition. So the effect of the curing is huge in 3D printing, especially in the first 48 hours. And the other thing is just, you can see leather smelter slag is actually a pretty good material. As you can see, the bonding is great compared to natural sand, as you can see from the ITZ here compared to natural sand here. So in terms of the rheology of the material, it is very important to look at the three different parameters, as I said, triangle of rheology for 3D printing. So shape and stability, so avoiding the formation of the layers after printing. So pumpability, so we can pump and extrude the material, or extrudability, and also buildability. So because there is no formwork to hold the material, so how many layers we can put on together before it collapses. And we use the rheometers in order to assess that. And we look at the yield stress development of the material versus time. And we need the initial good yield stress in order to make sure the material has got a good shape and stability, so it doesn't flow after extrusion. And also we have an upper limit, because if material getting too stiff, it's not going to be extrudable or pumpable. So there is a limit that we can use the material in terms of the yield stress. And on top of that, there's a buildability limit. So it's just growing yield stress of the material in order to the material can hold its self-weight without any collapse, plastic collapse, or elastic buckling. So we say the print window based on these from three boundaries of the shape, stability, buildability, and extrudability. And we want a material that doesn't cross the boundaries, these three boundaries. So if it's strength developing too fast, it's going to kind of pass the limit of the buildability, pumpability. And if it's developing very slowly in terms of the strength and yield stress, then the material would not be buildable. So we want something theoretically that just go parallel to the buildability limit, starting with a good shape and stability. Even if not that, we can wait a little bit until material gets some good strengths to be buildable. So that's fine. But the main concern is about the buildability and also pumpability. So, you know, and this buildability limit, it depends on each printing scenario, how fast you print, your layer height, and some bunch of other factors that for each job can be different. So if you're printing a house, which is 50 meter or 100 meter or 200 meter, the buildability limit is going to be different. If you're printing a vase, the buildability limit is very high because each lay probably take 1 minute or less than 1 minute for each layer. So based on those, and we can change the material and mix design, for example, changing the water to cement ratio, changing the superplasticizers, and another thing to see, like, if you are within those criteria, or are we just crossing the buildability limit or other limits of 2D printing. But one of the things that we have found out that using the rheometer as a tool in order to assess that is not really comprehensible, because some of those 3D printing mixes is very viscous. And because of that, some of the rheometers are not gonna be able to test those very stiff materials, and the result might get a lot of errors even if they do. So we need some other tools. So concrete rheometers is one of the tools. Unfortunately, we don't have access to it, and it's something that we can buy off the shelf, to my understanding. But there has been some development around the world in different research groups in terms of the concrete rheometers, which has higher capacity. They can measure very stiff material. But we can also use green compressive strengths. So similar to the compressive strengths of the hardened sample, we can make a mold and put the material in without any vibration or compaction. So just representing the 3D printing, and then put on the very small amount of load equivalent to the load of the successive layers of the 3D printing, and see that how the material develop in terms of the strain, and also in terms of any development of the cracks, etc. The other thing is just using the ram extruder. So and based on a piston that we can put the material in and just apply the pressure, and the material is coming out from the nozzle at the other end of the piston, and then based on the force versus displacement, we can figure out the yield stress of the material and its buildability and extrudability. So we discussed about the rheometer. We can measure static and dynamic yield stress and see that how the strength is developed. So if you look at the ram extruder, it gives you these kind of graphs, which, as you can see, the consolidation at the start, and then after that is get a plateau, which the material is getting out of the piston, which we use this plateau in some equations to get the yield stress of the material, and also at the end, which we have some compaction and dead zones that contribute to this force development. And also green compressive strengths, we apply a force as per time, ongoing, as I said, representative of what's happening when we are doing the printing, and based on that, we see, like, if the material can resist that load or not. Another work by one of other PhD students, Liming. He recently published a review about the effect of the nozzles in Journal of Automation in Construction. And today also I included some of the slides of some of the experimental work that he's been doing. Look at the effect of the nozzle designs in 3D printing properties. So we looked at the circular nozzle, the square nozzle, and rectangular nozzle with different aspect ratios, as you can see in this photo. And these are the results of each of those nozzles in terms. So we printed 2 layers side by side. And as you can see, the layer height and the width is different based on the nozzles that we use. And there might be some gaps developing between them when we printed 2 layers next to each other. We printed some small samples. Excuse me. And then we cut the samples to measure flexural strength, compression test, and tensile strengths. As you can see, based on the top of the nozzle that we use, the compressive strengths might be changing. So you can see like the nozzle 2, which is the square nozzle, give us the highest compressive strengths. But it's also different in terms of like flexural strengths and tensile splitting strengths. For example, the nozzle 4, which is the rectangular nozzle with the highest aspect ratio, the bonding between the layers is very high, and for that reason, when we do the tensile splitting strengths, which we apply the force at the boundaries of the 2 layers, we get the highest strengths. The size of the samples are the same, so it's not a effect of the size, but the bonding is much better. Another work that we've been doing on printing in a staircase, which we use 60% less materials in that staircase and passing the standard Australia for staircases. We are still working on that in order for structural design optimization and finite elements modeling, and hopefully we'll publish the results next year. And if I come back next year, I'll talk more about this project. And also another project using the macro CT scan, we printed lightweight concrete and we put the samples in macro CT scan. As you can see, there are gaps between so these are 2 layers actually, and so you can see that there is a very high interlayer porosity, and this is something that is very important, especially when we put the reinforcements between the layers. So there is a very high amount of the porosity. So any reinforcement, especially steel reinforcement, is going to be prone to corrosion because of the much better access to the steel, and the cover is not that good in 3D printing. So, these are the things that we need to think about when we are talking about steel reinforced 3D printed concrete. Mr. Chair, please let me know. I don't know, because of the thing that happened, how much more time do I have? I can just stop now for questions, or I can continue.
Sure, you can continue for next another 7 minutes, and I'll let you know in case.
Okay, thank you so much. So another research aspect that we are working on is the carbon utilization in concrete. So as I mentioned, we can recycle back that CO2 that's emitted during the cement production and put it back in, and mineralize it into the concrete. I'll skip this slide and also this one because of the lack of time. So essentially, there is a lot of CO2 that we need to remove from the environment in order to get to our net target for target of net zero by 2050. This is, as you can see, in the Australian context, 1/3 of the effort that we need to put in is all about the capturing CO2 in cement and concrete industry. So there are different methods that we can utilize CO2, emitted CO2, captured and utilize it in concrete. So it can be during the production, so for example, concrete mixing, which a liquid version of CO2 can be mixed with the material. And the CO2 curing, so especially for precast elements, so we can put it in the chamber and cure it with CO2. And as also, CO2 sequestration can happen to any concrete structures during its lifetime. It's very slow. They call it recarbonation, but the extent that they can get the CO2 back, it's in a short amount of time is pretty low. And the high CO2 uptake is going to happen in the CO2 curing compared to the other methods. That's why we are working on that. So essentially, what you do, you got some calcium compounds in your cement mix that gets reacted by CO2 that you introduce during the curing, during the mixing, and then you get some calcium carbonate. So that's calcium can come from cement or any other materials that's containing calcium. In this case, you can see the cement and CO2 just developing the carbonation product on cement grains. But what we have done, we provided a better vehicle for CO2 transportation inside the concrete. So if you're familiar with measuring the carbonation in concrete, it starts from the surface and it stops at some stage because they can penetrate more as the carbonation products build up and there is not much more space for CO2 to penetrate. But if the material is aerated, so we got some open porosity and permeability, then they can easily get inside the samples, and so they've got much higher CO2 sequestration inside the concrete sample. So for normal concrete, if the process is right, maybe you can get 12 to 15% CO2 uptake per mass of the reactive binder, mainly cement and other binders. But if you use it in the lightweight porous concrete as we've done, that can double that amount of the CO2 sequestration. So some of the result that I'm showing is the good work of our colleague, Dr. Gupta, when he was at UNSW as a research fellow. And now I think that Dr. Gupta is associate professor at IIT in India. So we looked at the foam concrete samples with fly ash, silica fume, and also biochar at different densities. And we introduced them into the carbonation. As you can see, the calcium carbonate product easily form inside the pores of concrete. And you can see up to 30% CO2 uptake can happen. And this is also depends on the mixer design, the density. As you can see, for example, the sample with silica fume, fly ash, and biochar. Biochar actually help with better CO2 sequestration as an additive. And they can get higher CO2 uptake in those samples. And also the carbonation depths, you can see the effect of the density. So the lower density that you got, the more porous the material gets, the higher depths of the carbonation inside the samples. And also the compressive strengths of the samples based on the degree of hydration, because we got the hydration and carbonation that happening at the same time. So there is a balance between these two. And based on the density, the hydration thing, and other factors, the compressive strengths of the sample are going to change. So we need to keep a balance between these two. And I think that's the end of my presentation. Sorry, I rushed it a bit at the end, but more than happy to take questions. Thank you so much.
Thank you so much, Dr. Reza. Thank you so much. You talked about sustainable and low carbon concrete. You talked about waste-based geopolymers, new nanocomposites for 3D printing. And you also touched a few topics on carbon utilization concrete. Dr. Reza, we have several questions from our participants. I would like to take them on their behalf. The first question is from Mr. Vishnu Prasad Prabhakar. He is asking, could you please comment on the repair of 3D printed structures that have been damaged from, for example, cracks from settlement or other physical damage? Additionally, does using a different type nozzle affect the rheology of concrete and its workability?
Sure. Very good question. So for the first part, the similar method for if any concrete cracks happening, the similar method we've been using it for those cases. And still, I think it's a very new topic. I haven't seen any research work on that. What is would be the best material and how we can, I mean, the first job is just to eliminate that. But if in just some cases that happens, what would be the best option in terms of doing it? But at the moment, it's just normal kind of epoxy binders for rehabilitation of those things. And in terms of the nozzle, I think that depends on the diameter of the nozzle, and also any other things, any roughness and things like that. It might affect the extrudability of the material. So, but the extent of that, which might be important, I'm not 100% sure, but